Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. It's our IMO series. This is a problem of IMO 1967, long list, problem 41. A line L is drawn through the intersection point H of altitudes of acute angle triangles, right? Which means the H is the orthocenter of the triangle, and the line L is passing through the orthocenter of this triangle. And proves that symmetrical images LA, LB, LC of L with respect to sides BC, CA, AB have one point in common, which lies on the circumcircle of triangle ABC. So basically the problem is saying that we have a line L passing through H, and we find the symmetrical lines of this line L to the three sides, and we want to prove that the three symmetrical lines are concurrent, and the concurrent point is on the circumcircle of the triangle ABC. Okay, so let's just draw the circle first. Okay. Then we draw the triangle. So we have triangle A, B, C here. Let's call the foot of altitude would be D, E, F, and this is H, right? And we have a line L that is passing through this triangle, passing through this point H, and we can find the symmetrical point of line L. And we eventually want to prove that the symmetrical line of the L to AB, AC, and BC are concurrent. So let's consider about the two symmetrical lines from the sides that line L intersect with. Okay, which means we're considering about the symmetrical line of line L to AB and line L to AC. And one property that we already learned and proved many times is that if we extend the altitude of a triangle and meets a circumcircle on a point, and we know that this point is a symmetrical point of orthocenter to BC here, right, to the side. Similar for this one, and similar for this one. Now we know that if we put the point here, M, N, K, right? These 3 points are the symmetrical points. Are the symmetrical points of H to BC, AC, AB, respectively. Right, that means the symmetrical line of L to BC, right? The symmetrical line of L to BC passing through the point M, because M is a symmetrical point of H to BC and line L passing through H. right? Then the symmetrical line L, symmetrical line of L to BC passing through passing through M, and also passing through the point that L and BC intersection. Similar for this case here, the symmetrical line of L to AB passing through this intersection point and also passing through this point K, right? That means we can simply draw this line here. And for this case, we know the symmetrical line of the L to AC passing through this intersection point, passing through this symmetrical point N. So let me just draw as this one. Must be here, right? And I draw it looks like this on purpose because we want to prove that this point is on the circumcircle, right? So I don't want to draw it on the circumcircle right now. We want to prove it. So let's call this point as P, right? Basically, what we're doing is that we find the symmetrical line of L to AB and AC, and we find these two symmetrical lines meet on a point P. And now we want to prove that this point P is on the circumcircle of the triangle ABC, right? Then we already know that K is on this point, K is on this circle, right? So if we connect KA, we connect PC, right? If we can prove if P, C, A, K are cyclic, then because the circumcircle of the triangle AKC and circumcircle of the triangle ABC are the same circle, that means P is on the circumcircle of the triangle ABC, right? So we are trying to prove that P, C, A, K are cyclic. And if you look at the figure, we know that K is a symmetrical point of H to AB. So this angle, let's call it alpha, equals to this angle, right? And because N is symmetrical to H, so we know that this angle, we call it beta, equals to this one. Let's call it beta, right? And this is beta, so this angle is beta. And because angle AFH is 90 degree, angle AEH is 90 degree, we already know AFHE are cyclic, which means angle BHF equals to angle A. Here angle A, I mean angle BAC. Right, and what is angle BHF? Angle BHF is alpha plus beta equals to angle A, or angle BAC, right? That's what we have here. Let's keep this, just keep this in mind. And now let's think about alpha, right? The question is, what is angle alpha? Look at the angle, think about that. If we can prove, because we want to prove that P, C, A, K are cyclic, right? That means if we can prove the circular angle that PC reference to, which is an angle PKC equals to angle PAC, then we just prove it. Or we can prove that angle PKA plus angle PCA equals to 180 degree. Or another way is to prove that angle KPC plus angle KAC equals to 180 degree, right? And basically we want to find the simplest way to prove that. Okay, now look at this angle, this one. Because this is alpha, so we know this angle is 2 alpha. Right? And if we look at this angle, this is beta, so this one is 2 beta. That means angle, let's give some letters here. Let's call it X and Y. Okay, so angle XPY equals to 180 degree minus 2 alpha minus 2 beta. And we know that alpha plus beta is twice of angle A. So alpha plus beta is angle A. So this one equals to 180 degree minus 2 angle A. Excuse me. Right. Now we get that angle angle XPY or angle KPN equals to 180 degree minus 2 angle A. Now let's connect NC, right? Because angle XPY is this one, it equals to angle KPN. And if we can prove that angle KCN equals to angle KPN, right? If we can prove that angle KCN equals to angle KPN, we proved that KPCN are cyclic, which means that P is also on the circumcircle of the triangle ABC, right? So what is angle KCN? Angle KCN equals to angle KCA plus angle ACN, right? And angle KCA, this angle, equals to, because AFC is a right triangle, so angle KCA is angle FCA, which is 90 degree minus angle A, right? So 90 degree minus angle A. And angle ACN equals to angle ABN. And because triangle ABE is a right triangle, so angle ABN equals to 90 degree minus angle BAC. So it equals to 180 degree minus twice of angle A, which equals to this one. Now we see that angle KPN equals to angle KCN. So KPCN are cyclic. Right? KPCN are cyclic. That means P is on the circle ABC. Now we have another question, that because we want to prove that P is a point is a concurrent point of 3 lines. We just proved that P is an intersection point of 2 lines and it's on the circumcircle. So we have to prove that the third line, which is a symmetrical line of L to BC, also passing through point P. And we already know that this line passing through this point and M, right? Basically, we just need to prove that this point, let's call it Z. Z and P are collinear, right? So we want to prove that P and Z are collinear. How can we prove that P and Z are collinear? Which we can still use the angle way, right? If we can find the angle of PM intersect with BC, and we already know that the angle MZ or angle LA, let me rephrase. We already know that the line LA and BC form the angle which equals to form the angle CZM, which equals to angle CZH, right? Equals to this one. And if we can prove that, if we can prove line PM and line BC form the same angle, then because line LA and line PM are passing through point M, that means, and they also have the same angle with line BC, that means these two lines are overlapping, right? So we want to prove that, which means we can think about the PM. Let's draw it here and extend it, for example, here. And then we want to find this angle. Right, we want to find this angle. And also, we want to find this angle, and then we can compare these two. Right. Notice that we already know that this point P is on the circle. So let me just draw it a little bit to revise it. Then it's easier for us to think about. Okay, it should look like this. Now let's think, how can we calculate for this angle, the angle CT, the angle CTP, right? The angle CTP equals to this angle minus this one. Right? But do we know about this one? No, we don't. So it would become kind of difficult to find the angle, to find this angle, right? But let's just think about that. This is the angle AKC equals to angle ABC, right? Angle AKC, this angle equals to angle ABC. And we know that AMPK are cyclic. So basically, this is angle B. Then we know the angle PMA, right? So the angle CTP is angle DTM, right? It equals to angle DTM, which equals to 90 degree minus this angle, 90 degree minus angle DMT, right? And what is angle DMT? Angle DMT is 180 degree minus angle PMD, right? Angle DMT is 180 degree minus angle PMD. Or say this angle equals to this one. So it equals to 90 degree minus alpha plus angle B. right? That is the angle CTP. That is this angle. This angle is 90 degrees minus alpha plus angle B. Now let's think about how can we calculate about the angle HZD, this angle. This angle equals to the angle DZ, what I wrote ZCZH, right? CZH. The angle CZH equals to angle DZH equals to 90 degrees minus this angle, the angle DHZ, right? 90 degrees minus angle DHZ. And we know that angle DHZ, right, the angle DHZ, that is the angle XHA, right, XHA. And we know that this triangle is congruent to this triangle. So the angle XHA equals to angle XKA, which is alpha plus angle B. That means these two angles are equal. So the angle CTP and angle CZH are equal, and that means the line PM intersect with BC line and form an angle equals to the LA intersect with BC form the same angle, right? And both lines are passing through the point M. That means LA and PM are overlapping. They're the same line. Therefore, the LA, LB, LC are concurrent on this point P, and this P is on the circumcircle of the triangle ABC. Okay? So, for this problem, we actually just did the angle chasing. Right? We actually just did the angle chasing. I think this problem can be a state level problem. Today, it cannot be the IMO in today's computation. Okay, I hope you like this video. See you in next one. Thank you.